We're again taking a look at complex numbers in today's further maths video, but we're going to look at a new form of expressing them. So we're now familiar with the modulus-argument form, and I'm going to show you almost an identity that can help you convert between that and what we call the exponential form. So we have a result that states that e to the I theta, where I is the imaginary unit, is equal to cos theta, and this makes the transformation from the modulus argument form, which you haven't checked out, I advise you look at first for obvious reasons, to this exponential form of a complex number. So if we have z equal to r e to the I theta, we have, this is our argument as before, and r's still our modulus. Okay, so we can represent complex numbers like this, which is going to come in very handy for something called roots of unity, and it also has some nice geometric properties on an argand diagram, but we'll look at that in a future video. For now, we're looking to derive a couple of results that the specification wants you to know using this result, this top result, this result star here. Okay, so we're going to look at that now. We're going to consider e to the I theta plus e to the minus I theta, and this is equal to e to the I theta plus e to the I minus theta. And the reason I've written it like that is now we can use our top result. E to the I theta is equal to cos theta plus I sine theta, and that gives us, in the first term, cos theta plus I sine theta, and then we get plus cos minus theta plus I sine minus theta. Now we consider what our sine and cosine graphs look like. Cosine starts up here, comes down like that. Anyway, rough sketch, the point is it's an even function, which means cos of minus theta is equal to cos of theta. Alright, you can see that because if we take a value of theta here, minus theta's here, terrible theta, but they give us equal y values. Okay, so we can just write cos of minus theta as cos theta, and the sine graph looks a little bit more like this. Alright, and this is what we call an odd function. We take a value theta here and we take minus theta. Well, these y values have the same magnitude but opposite signs, so sine's an odd function, which means sine of minus theta is equal to minus sine of theta. So writing that down and collecting terms gives us 2 cos theta, and we'd get a minus, so this is equal to minus I sine theta, and that cancels with that term, so that's what we get, and then dividing both sides by 2 gives us cos theta is equal to e to the I theta plus e to the minus I theta. Okay, so that's result 1 that you want to remember, but you also want to be able to show the derivation too. Now we're going to consider e to the I theta minus e to the minus I theta, and we're going to do a similar thing. I'm not going to write this intermediate step, so this is just equal to cos theta plus I sine theta minus cos minus theta plus I sine of minus theta, and again this is just equal to cos theta, this is equal to minus I sine theta, but we're subtracting here outside the bracket, so instead we get that these cos terms cancel out and we get 2i sine theta divided by 2i gives us sine theta is equal to 1 over 2i e to the I theta minus e to the minus I theta. Okay, and that's our second and final result we're going to look at in this video. Any questions on this, be sure to let me know in the comments. As I say, next video we're going to look at next further maths video, which will be Tuesday. We're going to look at roots of unity and expressing roots of polynomials in terms of this exponential form of a complex number. If you did enjoy this video, please be sure to like and subscribe, and I hope you stick around for the rest of the A-Level Further Maths series, and I hope to see you in the next one.